It's my pleasure to introduce to you Patrick Hayden, who's coming to us from Stanford. Patrick is like one of the leading sort of figures in the world, I would say, that has this ability to connect ideas from computer science and information theory to actual real physics, so kind of big problems that we think about in physics. And one of the things that I guess he's most famous for is this kind of connections between gravity and space-time and quantum information, and I think that's what he will speak to us about today. Before he was at Stanford, he was at McGill and at Perimeter, and he got his PhD as a Rhodes Scholar in Oxford with Eckert. And with that, I will leave the floor to you. Right. Thanks for coming.
Well, thank you for the invitation. It's been a really fun day getting to know a number of the people in the department here. And you have a beautiful space. And so, yeah, it's been a very enjoyable day. I'm going to try to tell you a little bit about this connection between quantum information and the structure of space-time. I've played a supporting role in this story, but most of the work I'm going to tell you about actually is not my own. I'm just going to try to give you a perspective on where we began and where we ended up, I think. And then I'll end by describing a little bit of the flow in the opposite direction, how some ideas from quantum gravity have had an impact on quantum computation. To begin, I would like to just stress that in the earliest days of quantum information theory, in the early 1980s, the people who were thinking about this were actually also interested in quantum gravity. There was a school that developed around John Wheeler, and a number of his students went on to pioneer quantum information. The man who coined the term qubit, Ben Schumacher, was an undergraduate in Wheeler's lab, who then went on to develop Schumacher compression. The first person to work out quantum teleportation was Bill Wooters, who was one of John's graduate students during that period. And so that's where quantum information in many ways began, but then it took off on its own and developed, well, quite spectacularly in many different ways, and potentially towards developing very important new technologies. And then 10 plus years ago, those two strands started coming back together again, and we realized that some of the deepest conceptual puzzles in understanding quantum gravity could potentially be illuminated by a light coming from quantum information. And so as a preamble, though, I'd just like to mention LIGO. So I always just get the shivers when I think about LIGO. Here we have this device, an interferometer with arms that are, I think, about 4 kilometers each, and capable of detecting shifts in the length of one arm relative to the other on the order of 1/1000th of the size of a proton. So humankind has achieved a lot. In our several thousand years of existence, and so we can look at the pyramids, we can look at the ceiling of the Sistine Chapel, but for sheer ingenuity and audacity, I think that it's hard to compare to what they built there. But the reason I'm putting it up is that I want to think a little bit about the process, the kind of processes that are detected at LIGO. And let's say the very first detection there were 2 neutron stars, each on the order of 40 times the mass of our sun, and they're orbiting each other. And so that produces gravity waves, and we see the gravity waves. They're registered by the interferometer. Each revolution is a cycle. And as they orbit, they emit radiation, the orbits decay, the periods shrink, and the amplitude of the oscillation grows. And what I want to focus on, well, first of all, yes, they did detect this, which is amazing. But once they actually start to merge, the signal goes away incredibly quickly, right? Like actually even before the signal, if we look at the x-axis here, these cycles are on the order of hundredths of a second, right? So imagine 2 objects 40 times the mass of our sun orbiting each other in small fractions of a second, but then they collide, an event of truly cataclysmic proportions, and it dies away, again, in hundredths of a second. And try to wrap your head around that, right? Let's just put this on a more human scale. Here's a swimming pool. there are some ripples, some waves on the top of the swimming pool. If there are no further disturbances, how long is it going to take for those ripples to die out? On the order of minutes, probably. This is just a swimming pool, right? So the ripples in space-time coming from that collision of the two neutron stars disappear completely in the space of hundredths of a second. How can that be possible? The story at the level of general relativity is actually pretty easy to understand. The disturbances actually fall into the black hole effectively, and that's where they go, and that's why we don't see them for very long. But if we're trying to build a microscopic theory of this process, what kind, that accounts for all the microscopic degrees of theory of that space-time, how could they possibly relax so quickly? And the answer turns out to have to do with chaos and non-locality, that those degrees of freedom have to be connected in a highly non-local fashion. There are limits to how quickly this can happen. Black holes saturate them. And we actually have simple models these days, solvable models like, for example, Majorana fermions connected with random quartic interactions, the famous SYK model, that reproduce this, what I'll call fast scrambling behavior. And so, I'll leave it at that for the moment. Well, actually, one thing I wanted to say is I just want to stress these two words, some models that have this very rapidly scrambling behavior, that could in some ways mimic the behavior of black holes. We can achieve it with random interactions of various kinds. It's a pretty generic phenomenon. And we'll come back to that later. So quantum gravity, this is a physics department, but I think various flavors of physics. So I'll just talk a little bit about what we mean by quantum gravity, why we care. Back in the day of Newton, everyone pretty much agreed that space and time were absolute, that there was a clock that everybody shared, and there was an instant of now that everybody agreed upon, and we all just marched forward in time. We were disabused of that notion by Einstein, who taught us that if there are two observers, one moving at a constant velocity relative to the other, then they will disagree on the meaning of now, the relativity of simultaneity. And a slightly older Einstein, not that old, just 10 years older, but older, actually discovered that space-time is dynamic, right? It's not just static, it's not just relative, but space-time responds to the matter and energy content of the universe. And what I'm going to try to convince you of today is that quantum information, in combination with more traditional tools of quantum field theory and quantum gravity, has taught us that space-time is just an approximation to something far weirder. And that far weirder thing, we don't know in detail exactly what it is, but we can make some, I think, quite reliable statements about some of its properties. So black holes, they're not so black after all. Your typical theoretical physicist on the left, scribbled on the blackboard, how he looked a little bit later, it's a Stephen Hawking course, who provisionally combined general relativity, our theory of the very big stuff, quantum mechanics, at least originally the theory of the very small, and predicted that black holes will not be completely black, they'll radiate very, very faintly. And that very, very faintly, it's important, it's useful to have some numbers in mind. A solar mass black hole will radiate like a black body about 10 billionths of a degree above absolute zero. And so in our universe, they're actually absorbing, right? The cosmic background radiation is orders and orders of magnitude hotter than this. But in empty space, they will radiate. And we can try to think about the process of black hole evaporation. And imagine that I've done something tremendously embarrassing that I don't want anyone to know about, but I wrote it into my diary. I want to get rid of that story so no one's ever going to read it. Where do I send my diary? I could try to burn it, but some diabolical spy might collect all of the ashes and the smoke and the radiation and reconstruct what I've written into it. I could send it into the black hole. Right? But Hawking teaches us that the black hole evaporates, so over time it shrinks, and there are only radiation products coming out. And he asked the question, does information escape from the black hole? And as stated, this seems like the most academic of questions, right? Like how many angels dance on the head of a pin? Like who really cares, right? About the fate of this diary falling into a black hole. But there are good reasons to care. And the reason to care is that it presents a fundamental conflict of principles between our two most basic theories of physics. On the one hand, we have quantum mechanics, and quantum mechanics, when you boil it down to its essentials, it tells us about a state space, and then the Schrodinger equation just tells us that the time evolution is unitary, right? We have to figure out what that generator is, what the Hamiltonian is, but the Schrodinger equation is just saying we have unitary time evolution. And in particular, information is preserved because unitary time evolution is invertible. So quantum mechanics says the information must escape, right? It's one of the most basic predictions of the theory. General relativity, well, it's Einstein's equation, it describes the shape of spacetime, and its most basic predictions are just the causal structure of spacetime, what can influence what. And the existence of black holes are very basic predictions of the theory. They're present in some of the simplest solutions we can write down. And so general relativity is telling us information cannot escape. And so we have a fundamental conflict of principles, not around the edges. We don't have disagreement around the edges, at the 11th decimal point in some theory. We have a fundamental conflict, in their basic structure that we should try to resolve. And we can make it even a little bit sharper that, it's one of the basic properties of quantum mechanical information that it can't be copied. This is what I always put in my very first assignment in quantum mechanics classes, the no cloning theorem. And so if it can't be copied and eventually ends up in the radiation, it should be only in the radiation. But like general relativity, you say it's inside the black hole, it should be only inside the black hole. And so now we have a very sharp conflict, right? It's either here or it's there. And you have to answer which one of these is correct. But if you would rather not, you could come with present a crazy idea, which is that both are true, right? And how can both be true? Both could be true if the inside of the black hole and the radiation are one and the same. That is in some sense the same stuff, right? That they are not independent degrees of freedom. And that sounds very weird, right? If we think about the ways, quantum, any kind of field theory, right? That the electromagnetic field can have a value here, it can have a value a light year away, and those are independent degrees of freedom that can only influence each other through interaction that is mediated by a medium in between, right? Where this would be a very radical statement. The inside and the outside are different descriptions of the same thing. Is there any precedent for such an idea? Well, first, I should mention this crazy idea dates back to 1993. Susskind, Thorlacius, and Uglum presented as a possibility. But we actually got used to this 100 years ago in quantum mechanics, right? That when we do classical mechanics, the position of a particle and its momentum are independent quantities, right? But we can describe the wave, in quantum mechanics, we can describe the wave function of that particle in the position basis. We can describe the wave function, the momentum basis, and those are just different descriptions of the same thing, right? If you know everything there is to know about position, meaning the position wave function, then you know everything there is to know about momentum and vice versa. This is what we call complementarity in quantum mechanics. And so there are now calculations, with some caveats, if we're going to try to talk about our own universe, but I'd say quite reliable calculations, that show if you have a black hole, you can imagine placing some sphere at some distance away from the event horizon of the black hole. So there's a radiation zone, and then there's a black hole interior zone. There's a large region inside the black hole for a sufficiently old black hole that is complementary to the radiation, in the same sense that momentum is complementary to position. And so this region I've called the island inside the black hole is encoded in the radiation. Any observable that you want to write down for the island can be written as an observable acting only on the radiation. Any action that you want to apply to interior degrees of freedom, you can perform that action by acting instead on the radiation. They are one and the same thing. And I'd say that this conclusion is really quite a profound discovery about the nature of spacetime, right? That it can be non-local in this truly astounding sense. And I should mention it was the first calculations that were done independently of this. There's a long sequence of results that lead to this, but the finish line where we blew the trumpets and so forth, Ahmed Al-Meri, who I believe is one of your colleagues at NYU Abu Dhabi, was one of the people to do that calculation. And the input, there are lots of ideas, and they're the traditional tools of high energy physics, so I'm not talking so much about them, but they're central. Path integral, the Euclidean path integral, sum over geometries, et cetera, But there are all these ideas that had to be injected from quantum information to get there. Quantum error correction, calculation of holographic entropies, intuition from random circuits, quantum chaos, and so on. I want to emphasize that this calculation is, I think, really quite robust, right? In particular, it's agnostic about the underlying microscopic theory of gravity. You don't have to assume that string theory is correct. You just have to assume, at the end of the day, that when you write down your semi-classical path integral, that the rules that you should apply are the standard rules that one would apply when we're doing semi-classical anything, right? And so at this point, I'd say this is the conservative description of what's happening. You have to have some special rules for gravity. It's going to behave differently than your usual effective field theories if you're not going to reach this conclusion. Okay. So this work was originally done in the context of the ADS CFT correspondence, and it's helpful to talk about it, if nothing else, than to be able to have some pictures that I can show you. And so, it's been around for 25 years, more, 30 years almost, and so I'm sure you've seen talks about it. This is a still conjectural, but well-founded correspondence between quantum gravity and asymptotically anti-de Sitter space in d+1 dimensions, and just the physics of a standard conformal field theory, some quantum field theory defined on the boundary. And the anti-de Sitter space has this time-like boundary, so it looks like you can actually draw this. You can draw the entire space-time as kind of living in a soup can, right? And the reason people like this is basically for the same reason if you when you do elementary quantum mechanics, if you like the infinite square well rather than the free particle on the line, it's mathematically and conceptually simpler, right? Discretizes various things. If we take a spatial slice of anti-de Sitter, it's hyperbolic space, and so this is an Escher rendering of hyperbolic space. Each of those fish is the same size in this space, but they're rendered, projected into the disk in this fashion. And so if you want to know the distance between any 2 points, you count the number of fish that you have to pass through. And in particular, you can see that the distance from any point in the interior to the boundary is infinite. We can also place matter deep inside ADS. So I should say that the geodesics are these, I think the fish swallowing, or the fish line up one after the other, and those are geodesics. So the white lines are geodesics there. If you place matter like a black hole inside ADS, that's going to deform the geodesics. So in particular, they might look something like this. Now, if this correspondence is true, it suggests a very, and suggested 30 years ago, a very deep question and hard question. How do you map observables from the bulk, from the ADS theory, out to the boundary? What does a localized observable deep in the bulk look like as a boundary observable? And a big part of the story that I'm going to tell is about trying to understand something about that. If we want to understand what an observable inside a black hole looks like outside the black hole, we need to understand how to map observables from inside towards the boundary. And to do that, it turns out it's useful to think about fine-grained entropy in the boundary theory. So there's a quantity called the von Neumann entropy. It's 0 if you have a pure state. It's non-zero if you have a mixed state. And in particular, if you have a pure state of the CFT system, which is defined on the boundary, so now this is the spatial boundary ring. If I choose a subsystem of the boundary, even if the whole boundary is pure, that subsystem will be described by a mixed state. And I can ask what its von Neumann entropy is, how many bits of uncertainty there are in that mixed state. And this is a well-defined quantum mechanical quantity. In general, calculating von Neumann entropys is really hard, because you have to maybe diagonalize the density matrix and evaluate minus the trace of rho log rho, minus the trace of the sum of the eigenvalues times their logarithm. So it's a complicated calculation. But in the ADS CFT correspondence, Ryu and Takinagi, again 20 years ago or so, proposed a shortcut. So if we want to calculate the von Neumann entropy of this mixed state in the boundary for this region A, it works out, we can get it up to a constant proportionality. I'm setting h bar and c to equal to 1, so 1 over 4 times Newton's constant. It's the area of some surface in the bulk. So which surface? Well, in this case, we think of surfaces. Well, let's start off. Let's think of surfaces that are anchored on the endpoints of A, and then they go into the bulk, and they can wiggle around however you want. And you find the one that has the minimal area, which in this case is the minimal length, right? And so that's going to be the length of this geodesic, and that's how you calculate the area. More generally, and this is going to be important for us, we don't actually prescribe that we anchor this surface. I'm going to call it gamma, so gamma A. But we don't prescribe that we anchor it on the endpoints. We use a topological condition, which is that if I take the region A on the boundary and I take my gamma, together they're the boundary of something in the bulk. So here you can see they're the boundary of this wedge right here. Okay. But equally well, I could have supplemented gamma with a circle, right? And then gamma union A would be the boundary of the wedge union the disk, right? But if I'm minimizing the area, there's no value in including this circle here, because that just adds unnecessary length, right? So in this case, we don't need a piece like that, but in general, we might need such pieces. And the language is that we say that the surface gamma is homologous to A. And we call this minimizing region here the entanglement wedge. So just an A. Okay. And so a big part of this story of the connection between quantum information and quantum gravity is understanding how to push operators from the bulk out to the boundary. And that story is what we call entanglement wedge reconstruction. So here I have a region on the boundary, which I call A, and it's the minimizing surface. So here I have the entanglement wedge, and I can imagine having an operator localized inside the entanglement wedge, some observable or some unitary operator, and I want to know how to represent it in the boundary theory, or whether I can even represent it in the boundary theory. And it's a long story that begins, back in 2006, I guess, for some special cases, that culminated eventually in a demonstration that any operator in the entanglement wedge, such that when you act with it, it wouldn't actually change the geometry significantly, so caveat, but any operator in the entanglement wedge can be represented as an operator acting only on the corresponding part of the boundary. So this operator phi1 in the bulk, there is a way to represent it as an operator on the boundary, but only in the red part. And not only do we know that it exists, but we know, at least in principle, how to write it down. This is one of the ways that quantum information came in. I'll wait to get there. Okay. So here, I again have an operator in the bulk, but I placed it deeper into the bulk. Okay, so it would have been outside the entanglement wedge that I drew the first time, but if I make a bigger boundary region with its corresponding geodesic, then this phi2 operator is now inside the entanglement wedge and can be reconstructed. Okay. But let's actually partition that region A into two parts, A1 and A2, and then have this complementary part A3, so the whole boundary is written as A1, A2, A3. So my original A is A1 and A2 together. There's nothing special about A1 and A2. I could have used A1 and A3, or A2 and A3. Any one of those would have been fine. And so I actually have multiple ways to push this operator phi2 out to the boundary. And in fact, I don't need the entire boundary. I can throw away, in this case, 1/3 of it and still recover the operator. And if you imagine that this is the operator, say the sigma z operator for some spin located at that location, or the sigma x operator, I can push both of them out. And so I can push a qubit, like a quantum mechanical information out to the boundary, right? Some non-commuting observables for some localized degree of freedom. And this may remind you of something, and so I'll just make a brief digression. This is actually a very exciting time in the theory, in the world of quantum error correction and fault tolerance. That just in the past few months, various groups have been putting out papers demonstrating quantum error correction in the sense that they take a logical qubit, they encode it into multiple physical qubits or multiple, not necessarily qubits, some kind of degrees of freedom, and then use error correction techniques and prolong the lifetime of their logical qubit. Right? So this is something that theorists proposed as a possibility back in the late 1990s. It is now actually happening. You can quibble about whether it's actually happened or it's going to happen 2 months from now, but this is, we are right on the cusp. And what is quantum error correction? It's the ability to protect quantum information from various types of corruption, right? What do we have going on here? Oops. We have some information deep in the bulk, and we can protect it from various forms of corruption, from losing 1/3 of the boundary region. And so what this teaches us is that the map, or that the bulk is represented in the boundary as a quantum error correcting code. And just that realization was quite profound, because it allowed us to then deploy the machinery of quantum information and quantum error correction to the study of quantum gravity. In particular, there are like non-commutative Bayes rules that you can use to actually perform quantum error correction. And that's the kind of map that you actually need to map the bulk to figure out how to map about bulk operators in the boundary. And so it gives you not just some conceptual leverage, but some calculational tools. So with those bits and pieces, we could try to actually analyze an evaporating black hole. And so here I have a black hole. It's supposed to be sitting inside of anti-de Sitter space. And when people do ADS-CFT, usually they define reflecting boundary conditions on their boundary. And that's actually problematic in this setting. And the reason is that even though there's an infinite amount of space between any point in the bulk and any point on the boundary, there's time dilation as well. And the time dilation in the bulk is such that a signal can propagate from any point in the bulk to the boundary and back in finite time, even though it's covering an infinite distance. And so if there's a black hole in anti-de Sitter space, it will radiate. Its radiation will hit the reflecting boundary condition and come back in finite time, and the black hole is just going to come to equilibrium and it's not going to evaporate. And this is actually an obstacle for a long time to using ADS-CFT to think about evaporating black holes, but you could just say, well, let's talk about an absorbing boundary condition. And if you impose an absorbing boundary condition, then you get an evaporating black hole. Actually, hold on a second. Yeah, okay, good. But to do that, we actually need a little bit of a generalization of this Ryu-Takeyanagi formula. In particular, we need a generalization that's going to be able to handle large amounts of bulk entanglement. So remember, in our bulk theory, this is some space-time, and there are quantum fields in that space-time. And the quantum fields themselves could be entangled with each other. And the Ryu-Takeyanagi formula just gives you a universal formula for entropy, independent of those, how many fields there are or what state they're in, and so it can't be quite right. And so this generalized formula, it measures only geometric entanglement. So just to guide you through this picture, my boundary region now in this picture consists of two pieces, two intervals that are disjoint, and the entanglement wedge is this region in the middle. And the green parts are the minimal surfaces gamma. Okay? And so the original Ryu-Takeyanagi formula, it only depends on the area of gamma. It doesn't in any way depend on the matter content, right? So that can't be quite right. What you need to do instead is that you have to say that the entropy of this boundary region A is going to be the area contribution plus the entanglement of the bulk fields between the entanglement wedge, which is A, there's A and the rest. And so you include that extra contribution, and then you minimize over all the surfaces. And that doesn't look like a big change, but it's going to turn out to be crucial. All right, so what happens with an evaporating black hole now? So we have an absorbing boundary condition, and how do we build an absorbing boundary condition? We imagine there's a bath, right? So this region, this R, is not part of the geometry. It's just some system which is acting like a bath. And so the radiation degrees of freedom can get lost into the bath. That's the region R. And we're interested in the fine-grained, the von Neumann entropy of this region. And we want to know what it does. Well, for early times, it turns out that this surface here just is the surface that separates the bath from the rest of the system. And so the entropy of the bath, or rather the entropy of R is just the entropy of the bath. And so if we ask how this von Neumann entropy behaves as a function of time, it just grows. And this is just capturing the, this sounds a little bit complicated, but if you think about your very kindergarten picture of black hole evaporation, that there are entangled pairs at the horizon, one of them falls into the black hole, one of them comes out, they're entangled. And so if one of them falls in, and the one that falls out is entangled with the one that fell in, there's one bit of entropy that came out, right? Entanglement entropy. And so that very simple-minded picture would say that as a function of time, this entropy should just climb monotonically, right? And that's basically the kind of calculation that Hawking did way back in the day. And so we recover that simple-minded picture. But things change once the black hole has roughly half evaporated. So its entropy has fallen by a factor of 2 from wherever it started. And what one finds at that point is that a new minimal surface appears. And I've just drawn it right here in green. And this new minimal surface sits just inside the horizon of the black hole. And that makes all the difference. This is a little bit when I first showed you the calculation of the entropy. I said you could put a circle inside the bulk, but it didn't help. In this case, it's going to help to put this circle inside the bulk, which is not connected to the rest. And the reason is that now our entanglement wedge R is going to consist of two pieces, R1 and R2. And they're highly entangled. Remember, we had this picture of Hawking pairs, one falling in, one falling out, that were highly entangled with each other. But if we include both halves of that Hawking pair, we get something that's quite pure, right? That's not as close to a pure state, right? So that if I have half of an entangled pair, it won't be a pure state. If I have both halves of an entangled pair, it will be a pure state. And so all of the Hawking pairs that exist that have been absorbed into the bath are in R2. Those that fell in are mostly in are in R1. Those that fell in are in R2. So together, they're going to be close to pure, and the bulk entropy is going to be small. And so in this regime, the entropy that gets calculated is dominated by the area of this minimal surface, which is the horizon area of the black hole. And the horizon area of the black hole, as the black hole evaporates, shrinks, right? And so this calculation tells us that the entropy is going to go up, and then it's going to go down. It's actually just telling us that the evaporation of a black hole in n-tie de Sitter space behaves just like the evaporation, or the burning a lump of coal. If you were to look at the fine-grained entropy of a lump of coal as we set it on fire, or rather say the evaporation products, it would, or the coal itself, just talk about the coal, it could start off in a pure state, and as it starts to burn, it emits radiation products and other stuff. And what's left behind is highly entangled with the stuff that comes off. But eventually, as the coal burns away, there's less and less stuff, and eventually there's nothing left, and so there can't be any entropy anymore. And so it's telling us that black holes, strange, even though they're very different objects, behave the same way. And this calculation I want to emphasize is one that at this point is really just a calculation in effective field theory. It doesn't, it's just a semi-classical quantum field theory calculation. But it has a very interesting consequence. Because the black hole interior, what I was calling R2, is now part of the entanglement wedge of the radiation, right? And if the black hole interior is part of the entanglement wedge, that means the black hole interior is encoded in the radiation. This entanglement wedge reconstruction story I was telling you about before says exactly this. An operator inside R2 can be encoded into operators acting in capital R, in the bath. And so any operation you want to perform on the interior of the black hole, you can perform it by acting on the radiation. Any measurement you want to perform on the interior of the black hole, you can perform it by acting on the radiation. And that is a summary of what I wanted to tell you about that story. I think that I saw that Ahmed is going to be giving you a colloquium in January. I suspect he's probably going to tell this story in greater detail. So I just wanted to kind of sketch out how it works. And I wanted to emphasize, I just wanted to sketch out the actual calculation, which I'll tell you about, but the connection to error correction and this profound fact about the non-local structure of spacetime that it requires us to accept. As I said before, the calculation has now been done in various forms. It was originally done in anti-de Sitter space, or asymptotically anti-de Sitter. It's now been done in various forms of asymptotically flat space. It has not been done in de Sitter space. And so it's conceivable that things are different in our universe with its positive cosmological constant. Okay. So now I want to change gears a little bit and tell you a bit about a flow, a story that goes in the opposite direction. There's been this large injection of ideas from quantum information into quantum gravity, and it's been quite successful. But there's also been a flow of ideas from quantum gravity into quantum information. And one place that happened recently in a paper that I wrote this year is in this business what's called position-based cryptography. So one of the things quantum mechanics gives us is it allows us to perform various cryptographic tasks that might otherwise be impossible. You may have heard of quantum cryptography, key distribution. So something you might want in most of the tasks that, the way that cryptography works, most of it these days, the fuel for the cryptography is secrets, right? That if you and I share a secret, we can use that to communicate, we can use that to authenticate, and so on and so forth. But you might want to base your cryptographic security on something other than secrets. And one thing that you could imagine basing it on is position, right? And so here at the White House, I have a Pentagon. Maybe it would be nice to design a protocol such that only people in the White House and the Pentagon, they could there'd be communication, but you could only decode the communication if you were in the Pentagon or the White House, right? So position-based cryptography. And one of the interesting things about position-based cryptography is that in the absence of quantum mechanics, it's provably impossible. Not just information theoretically impossible, but most of our modern cryptography is based on computational assumptions. If you've heard of RSA and so on, it's computationally impossible. There's just no way to make it work. So you might ask about whether quantum mechanics might help. And we can try to think about what a position verification protocol would look like. How can we check to see if somebody is where they claim to be? And so here, let's do this in 1 + 1 dimensions. And somebody claims to be at this point in space-time, the yellow point, okay? How do we verify that they're there? Well, someone at C0, two individuals on either side could send messages at the speed of light, and the person in the middle would have to intercept those messages, perform some action, and then send out the information again at the speed of light. And if they were too far to the right, if they were too far this way, then the message coming from C0 would take too long and they wouldn't be able to complete it. If they were too far to the left, the message from C1 would take too long and they wouldn't be able to complete the task. And so this kind of looks like a basic primitive, a way that you could try to actually confirm that someone is where they claim to be. And to give you an example of a protocol that one could, to be concrete about it, Q could be a bit, 0 or 1, and the message from C1 could be a qubit, right? A two-dimensional quantum system. And that qubit could be either in the sigma z or the sigma x eigenbasis, right? And q just tells us which one it is, right? So there's a message, which is b, but the person here doesn't know, if they don't receive the message from C0, whether that message is in the sigma x or sigma z eigenbasis, two complementary bases. But once they receive the label of the basis, they can change basis, and what they're supposed to do is send the value of the bit to the two receivers, who will then compare to make sure that this guy did what he was supposed to do. Now you might think this would be secure, but it turns out it's not. That if someone wanted to cheat, that they could get their friend, bring their friend over, and stand outside. Here I've grayed out the region that they're supposed to stand in, and maybe I'm cheating, so maybe I'm here and my friend is over there, and they intercept the messages. They act locally, and then they just send part of whatever output of their local computation is to receiver R0 and one to receiver R1, and there's some local processing. And so they never actually set foot in the location they're supposed to be. And it turns out that if they share entanglement, they can crack any protocol that you could ever imagine. And it uses some fancy versions of teleportation. We can talk about that. But it can be done, and this is very surprising. Now, there's a huge gap in our understanding, however. So for this little protocol, that I described right here with the basis, if you run it n times, we know that it's going to take at least order n entanglement, right? Not too much, yeah. But to attack a general protocol, the best protocol we have takes an exponentially large amount of entanglement. And that procedure was demonstrated 13 years ago. No one's managed to improve upon it. And so there's hope in the world of quantum computation that you can actually realize secure position verification and position-based cryptography using quantum mechanics, because if the amount of entanglement required is exponentially large, it's never going to happen, right? You just run a protocol with 20 qubits or 100 qubits, and it's never going to happen. But no one knows really could a better protocol exist? Well, let's think about ADS-CFT. And this is now going to be a thought experiment, not a real experiment. I'm going to imagine that deep in the bulk of ADS-CFT, there's someone sitting with a quantum computer. Okay, deep in the bulk. And the two messages from C0 and C1 are going to be sent in from the boundary at the speed of light. With this quantum computer in the bulk, we're going to process those messages, and we're going to send messages back out. And you can see that the geometry here, the output points are rotated 90 degrees relative to the input points. Okay, that geometry is actually important. And it's important because it leads to a very interesting relationship between the bulk and the boundary causal structure. In the bulk, there is this point, the yellow point, where the computation happens, right? It's in the future of C0, so that whatever happens at C0 can affect the outcome. It's in the future of C1. It's in the past of R0, so that it can affect what happens at R0. It's in the past of R1. Okay. But let's look at the causal structure here on the boundary, because the bulk theory is supposed to be dual to a boundary theory, which is just a quantum field theory. Okay. And so we should be able to describe what's happening in the bulk purely in terms of the boundary. And so if C1 is to affect the outcome, then R0 and R1 should be in the future light cone, or should be in the future of C1. So that white region is now the allowed region for where the computation could happen. It should also be in the future of C0. So I should say I unwrapped the cylinder of the boundary, so I've identified the left and right sides. So the future of C0 is this region over here, and this region over here. And so now I have two white regions that are the intersection of the futures of C0 and C1. It should also be in the past of R0, right? So that whatever happens can affect whatever gets sent to R0. So so now my allowed region is this white piece here, but this white piece here is not in the past of R1. Right? And so in the boundary, there is no point which is in the future of C0 and C1 and the past of R0 and R1. So there's no there where the computation can happen, right? So that computation, from the point of view of the boundary theory, has to have become some kind of distributed computation, right? What was localized in the bulk becomes distributed. And so here I've just actually drawn those four light cones, and then partitioned the boundary, the slice of the boundary space-time into pieces. And what's happening in the boundary theory can be interpreted as a non-local distributed computation of exactly the kind that you need to crack the position-based cryptography, right? That there's some information that gets sent in from C1, so it's in the future of C1, for example, and then from there, there's some time evolution that happens, and some of the output passes to this region, which is in the past of R0. Some of it passes to this region, which is the past of R1. And so each of the space-time regions in the boundary that contain a yellow dot or a red line can be identified one-to-one to one of the portions of this computation right here. And so if I could simulate the boundary theory well enough and effectively enough, then I could get a distributed computation that I could use to crack position-based cryptography. And the amount of entanglement being consumed is not exponential in the size of the input in this case. It's just linear. So I'm not going to, there's not time to go into the details, but I'll just tell you that we did develop this attack, right? That we didn't actually use ADS-CFT. We're motivated by ADS-CFT, but there are quantum error correcting codes called holographic quantum error correcting codes that have many of the properties of the bulk boundary duality. And then we had to take the bulk computation that we want to perform, push it out to the boundary, and then simulate it appropriately, in such a way that we could run it on a quantum computer. And it turns out, and this is just kind of either unfortunate, surprising, good or bad, that if we take the very best methods existing for simulating one Hamiltonian using another one, which is the kind of thing that is actually, these days, analog Hamiltonian simulations happens in the lab all the time. We use the very best methods. We don't quite get there, right? So we don't manage to actually get a protocol. That if the best, we actually had to invent new protocols that were better than, but we did our very best. One of my co-authors, two of them are like the very best at this, building these simulations anywhere in the world. So I think we did pretty well, but we didn't quite get there. So if simulations slightly better than we can construct existed, then we'd be able to crack position-based cryptography. As it stands, we just have this conditional statement. If position-based cryptography is secure, then Hamiltonian simulation can't get much better than as it exists right now. Okay. Well, I'd like to end by just asking a little bit of a question. What is space-time made of? So at the beginning, I presented this fundamental conflict of principles between quantum mechanics and general relativity, and as a strategy for making progress in physics, right? Historically, it has been it's often been successful to try to look at your competing theories. You find fundamental conflicts of principle, and then you tease out the resolution of that conflict, and that that gives you some insight into what comes next. And that's one of the reasons people were interested in the information problem, because there was an expectation that if we were to resolve the information problem, it would give us an indication about what the underlying structure of the theory of quantum gravity. It didn't quite pan out that way, right? As I've been telling you, it's a robust calculation which doesn't really care that much about the microscopic theory of quantum gravity. So it taught us some amazing things, but it didn't tell us that string theory is right. It didn't tell us that loop quantum gravity is right or wrong, or what. It just said, and so it's good and it's bad. And so we still don't know what space-time is made of. But in these examples, we're seeing space-time as an emergent, or at least some features of space-time as being emergent, right? Dynamical gravity is emergent in ADS-CFT, it's emergent in SYK. One of the spatial dimensions, is emergent, and so on. And, well, you all know this, but the energy scale for quantum gravity is about 10 to the 28th electron volts. the Large Hadron Collider energy scale is about 10 to the 15 electron volts. We're never going to build a collider big enough to answer this question. What is the microscopic stuff of quantum gravity? Maybe from cosmology we're going to get some hints, but yet, how are we ever going to make progress? Well, let's think back to that very early slide where I was emphasizing the fact that we could recover many of the features, the gravitational type features, emergent space, fast scrambling, dynamical gravity, in these theories that had pretty generic definitions, right? Like this SYK model of fermions interacting with random couplings. It doesn't seem very special. And so there's an expectation lying around that space and gravity can emerge quite generically in strongly interacting many-body quantum systems, provided they satisfy some basic conditions at the outset. However, strongly interacting many-body quantum systems are extremely difficult to solve, right? And so we can solve, in some special cases, we can solve them. We use these random interactions to simplify things. We use supersymmetry to simplify things. But there's a whole world of theories that we just really have no idea what's happening in them. And they may actually have emergent gravity. We don't know. And this is where experiment can actually come to the rescue, and in particular quantum simulation. And so I wanted to just point to a paper. When I selected this paper for my talk, one of the authors is Emily, your new professor. I swear I did not know she was here when I selected this. It's not a plug, it's just a coincidence. But in the not too distant future, I think it's realistic for us to be building quantum simulators that will have programmed interactions that will demonstrate, that will have effective descriptions that are effectively gravitational, and we'll be able to learn what kind of conditions are necessary in order to see emergent space, in order to see emergent dynamical gravity. And a step in that direction is just this paper here. I really like it. Emily and her collaborators had ensembles of atoms trapped. I guess they call them atom clouds, yeah. So a cloud of atoms, another cloud of atoms, another cloud of atoms in a linear array. So they interact, a priori you'd expect them to interact nearest neighbor, but they could actually trick the clouds into thinking that they were in different geometries. And so in one instance, they tricked that linear array of atoms into thinking they were in a ring. And here's the best reconstruction of the actual geometry. My favorite one is this one, is a D over here. It tricked the atoms into thinking they were in a Mobius strip, even though they're just in a linear array. And so this is just the very beginning, but I really think this is something that's going to happen. And it's a beautiful irony, right? That even though it's going to be extremely difficult to get detailed experimental information about the microscopic constituents of our own spacetime, we'll be able to actually make toy spacetimes and see how they emerge and how they behave. And that might give us insight into the origins of our own. Thank you for your attention.
Thank you, Patrick. Questions?
In the position-based cryptography, the two C1 and C0 to begin with, they decide at the last moment what message to send, or do they have to agree in advance? Because if they have to agree in advance,
Yeah, so
there is a cause of connection.
The way to think about it is that somebody claims, let's think of them being think of the honest case. Somebody claims that he is at this location in space, will be at this location in space-time. And so there's a team of referees that are going to try to probe him. And the way that they probe him, they say, okay, someone at this location, space-time location C0 is going to send you some piece of information, like it's the choice of basis. Someone from C1 is going to send you a qubit, and you're going to have to change the basis of that qubit. So they all agree ahead of time on what's supposed to happen. And if he's at this location, he performs the transformation, he sends the outputs to R0 and R1, and then the referees get together and they make sure that the output is what it's supposed to be. Does that answer the question?
Yeah, so my question was whether this previous agreement would leak information.
Oh, I see. So there's an assumption in all of this that we can make free choices at different points in space-time. And so this is similar, this assumption is implicit, say, when we do Bell inequality experiments, right?
Okay, so that's the previous agreement is only on the protocol, but then C0 and C1 will send some random information. Some random bit decided at the last moment.
C0 and C1, for the protocol that I described, their actions are coordinated because the choice of basis prepared at C1 depends on C0. So at some time in the distant past, they could have agreed, or they could have just shared some random numbers, or they could have, you could say they just have some entanglement, if you like, and they just using the entanglement they can measure the entanglement, like a L pair 0, 0 plus 1, 1, and get a random pair of random correlated bits. And those, according to quantum mechanics, aren't correlated with anything else in the universe. And so they could use that as their coordination mechanism to start off.
So a spy that is in the past.
It doesn't even need to be, if they share the entanglement, they can make all their choices right when they send them.
Yeah, so you were saying at the end, maybe it's generic for strongly interacting many-body quantum systems to be dual to something like gravity. But there's another piece of lore which goes in the opposite direction that says it's actually very difficult to find quantum theories that have that property, in particular in higher dimensions that we understand maybe a little bit better. You need like a Hubble field theory with a particular spectrum, it has to have a large gap, large n, and probably has to be supersymmetric, or at least there's a conjecture that says it. So I guess the question is, how would you know? I mean, suppose we get very good at simulating the systems or just building them and studying them. How do we know whether or not they're dual to?
Yeah, so I haven't worked very hard on this, but yeah, so it's a very good question. Like if you're working with pencil and paper, right, then you actually have some logical sequence of logical steps that gets you to some some metric or something like that. In the absence of such things, you could imagine sending probes, right? I think you would expect to see some kind of behavior that looks like scattering events that have no reason to exist if you just look at the boundary theory. And so that might be some way to detect some geometry. There are, let's pause and think for this a little bit. So you could, this is sort of similar, like looking for signatures and correlation functions. But like my immediate response is that I think you'd be trying to look for some spurious scattering type behavior, but that's pretty primitive and it might be hard to find, right? Like it's like you don't know how, it's like you're trying to aim to laser pointers at each other and you don't even know how to aim them or which you could spend a lot of time at it. There is this paper, which I think is a very interesting paper on, what do they call it, size-winding teleportation, like the relationship between traversable wormholes and teleportation. And it has a bad smell around it now because there was an experiment done by the Google group that was ridiculously overhyped, and they said things that they really should not have said. But there's a particular signature, which is a necessary condition that there's going to be geometry, which is about the way I can remember how it works. But this size winding property that makes the teleportation function. And so in the case of, like if you prepare a thermofield double state in a gravitational theory, that corresponds to some wormhole between the two, the two asymptotic regions. And through appropriate couplings, you can make that wormhole traversable. And if that story remains true in your, in this theory, without actually knowing the details of the geometry, there are certain properties that have to be, that could be verified. And so that's an example of something that, of a test, right? It's not a sufficient test, but it becomes a necessary test. And I think it would be very interesting to try to actually systematically write down more examples of such things. As you can see, I haven't thought about it very hard, so I don't have very good ones. But I think it's a very interesting direction to go. It should be done.
Can you please go back to the early view graph, the first view graph where you showed the island?
Yeah.
Basically, I'm trying to correlate what I heard right now about the anti-de Sitter space for a black hole.
So do you mean this one or earlier?
And earlier, the very first one that shows an island.
Yeah. This one.
Yeah. I'm trying to, my understanding is that the picture that you have there, this one, it shows an island. This is for an anti-de Sitter space?
It is. It was originally calculated in anti-de Sitter space, but it has it's since been done just looking at the path integral and realizing that you didn't, so it's easier to think about and to draw when you're doing an anti-de Sitter space. There's a sort of very geometrical story, but the same kind of, well, I should say this picture does not require anti-de Sitter space. The story that I told was in the context of anti-de Sitter, but after it was originally done, it was generalized beyond.
The reason I have some difficulties, in the back of my mind, I tried to correlate this with what I learned many years ago about the Schwarzschild metric, as opposed to the anti-de Sitter. And in the Schwarzschild metric, this island simply cannot exist because everything just sinks into the singularity. Everything inside the Schwarzschild radius sinks into the singularity. You're not going to have an island. So I'm trying to understand.
Oh, I see. Yeah, so it eventually hits the singularity.
Yeah, yeah.
Yeah, so I didn't say in detail when I described my entropy formula what, in the case of dynamical spacetime, what surfaces we should be minimizing over. And we should be looking at all space-like slices of the spacetime and extremizing the area over all over surfaces in every possible space-like slice, and then taking the minimum over the extremized ones. And so there, what you get is you get space-like slices, like they call these the nice slices, that that go into the black hole. And capture, well, yeah. So you can make space-like slices that include almost all the outgoing radiation, and also include the interior of the black hole, but before the singularity. Right? In the Penrose diagram, the singularity is space-like, and so you can just make a space-like slice that doesn't actually touch the singularity.
I'm trying to understand it from a physical point of view.
But it's not a physical, it's not an island where you crash your ball, right?
Oh, yeah.
It's just a mathematical.
Oh, yes, sorry, it's language,
like
yeah. It's a surface in a particular space-like slice.
In this language, I understand it. What I'm trying to do in the back of my mind is I'm trying to get some physical image of what it could be.
So cut a Penrose diagram at fixed time, and there is a region inside that cannot be reconstructed from whatever system sits outside and is holographically describing space-time, but you have to go and look at radiation to reconstruct,
yeah,
at the early radiation.
Yeah.
It's all
But I think since it's already 6 minutes over and we can continue the discussion at the reception, let's thank Patrick again.